Multicentric study on a new extracorporeal vacuum assist device. To optimize cardiopulmonary bypass, the Avado system. The aim of the Avado system is to optimize cardiopulmonary bypass through 4 steps. The minimization of hemodilution in CVP, which leads to the reduction of cell-mediated pro-inflammatory effects, easy maintenance of plasmatic pressure and high hematocrit hemoglobin levels during cardiopulmonary bypass, with decreased need for transfusions. A true separation of blood from extracavitary suction, since, as we know, in traditional systems, suction and reinfused blood is a very powerful activator of CVP inflammatory processes. In a Avado system, such suction is truly separated and then processed through cell saver to be reinfused later. Third step is the reduction of mechanical damage to red blood cells and inflammatory activation. The Avado system avoids the use of the roller pumps, which are themselves a pro-inflammatory factor, for intra and extracavitary suction, thus reducing blood cell damage. Fourth step is the increased intraoperative flexibility and surgical versatility. Miniaturized cardiopulmonary bypass does not allow big amounts of air into the circuits, thus limiting its use only to a specific kind of operations. The Avado, being an open system, is much more flexible and can be safely and reliably used in a wide range of cardiac operations. Let's take a look at the Avado system. It must be emphasized that the Avado is not to be considered a miniaturized CVP, but an integrated system designed to optimize the extracorporeal circulation. The system components are the Admiral, which is a phosphorylcholine-coated oxygenator that requires low priming, has a limited contact surface, and contains a venous reservoir as well as an accessory independent cardiotomy reservoir, which allows separation of pericardial suction blood. The Harmony Smart Suction System, which allows automatic auto-regulation of pumpless extracavitary blood suction with rates and pressures depending on whether suction is required for blood-air surfaces, skimming, or fluids pooled. Vacuum-assisted venous drainage, VAVD, and pumpless intracavitary blood suction are managed by a digital vacuum regulator that is connected to the oxygenator reservoir. Retropriming can be performed. Pediatric circuits with 3/8" tubing for both arterial and venous lines are used. No use of roller pumps for suction lines, for which all these components make the Avado system. You can get a better idea of the system from this slide that compares conventional CVP and the Avado system. As you can see, roller pumps are not used for suction blood. The intracavitary suction blood goes directly to the oxygenator reservoir, while the extracavitary goes to the separated cardiotomy, completely independent from the oxygenator reservoir. Our study, we prospectively randomized to either Avado or conventional CVP 324 patients undergoing open chest surgery for a wide variety of cardiac conditions. Patients with severe renal or liver failure or presenting major clotting function problems were not deemed suitable for randomization. Similarly, patients undergoing emergency or redo surgery, those requiring circulatory arrest or CVP times above 2 hours were not considered for the study. Of the 324 eligible patients, 25 required blood transfusion prior or during surgery, and 38 showed procalcitonin levels greater than 0.5 nanograms per milliliter. Since the measurement of haptoglobin, a major index of hemolysis, can be significantly affected by high procalcitonin plasma concentrations, this group of patients was also excluded from the study. Therefore, 121 patients were included in the conventional CVP group, and 140 subjects were included in the Avado group. The two groups were similar with regard to cardiac operation and the cardiac condition, Euroscore, New York, and Canadian class, as well as to age, body surface, preoperative hematocrit and hemoglobin levels, mean CVP and aortic cross-clamp duration. In all patients with the Avado system, I would like to underline, surgery could be completed without need to switch to conventional CPP. In both groups, the Admiral oxygenator was employed. For all operations, we used the same arterial and venous cannula. Obviously, diameters were depending on the patient's VSA. And neither cell savers or hemoconcentration or hemofiltration devices were used. Priming solution was the same in all patients. Systemic anticoagulation was obtained by sodium heparin titrated to obtain an ACT of 480 seconds before initiating CPP. All operations were performed by median sternotomy and under moderate hypothermia, 34 degrees, using anterogrador selected blood and a coronary blood cardiopulmonary with St. Thomas solution at a temperature of 408 degrees. All patients received tranexamic acid protocol. Hematocrit and hemoglobin were measured on blood samples obtained before starting CPP as well at 5, 30, and 60 minutes thereafter. To assess the extent and the presence of hemolysis, free hemoglobin and haptoglobin plasma levels were also measured at the same time. Haptoglobin is a plasma glycoprotein that binds free hemoglobin and decreases during intra or extravascular hemolysis, but also in association with other pathological situations such as bacterial infections. These in turn can be detected by elevated levels of procalcitonin. Consequently, patients with procalcitonin levels exceeding 0.5 nanograms per milliliter were not considered suitable for the analysis. Blood loss, along with the total volume of transfused blood derivates, was measured hourly in the 12 hours after surgery and daily afterwards. An arbitrary hemoglobin level of 8 was used as a cutoff for transfusions. As I was saying before, both free hemoglobin and haptoglobin plasma levels were recorded in the two groups 30 and 60 minutes after the onset of CPP. Values are expressed as a percent change relative to the control values recorded at the beginning of CPP. In this slide, you can see the behavior of free hemoglobin plasma levels in the two groups during CPP. The increase of free hemoglobin was significantly greater in the control group than in the Avado group. In fact, compared to the values recorded at the beginning of CPP, the increase of this parameter after starting extracorporeal circulation was respectively 20.38 and 7.01 at 30 minutes. You can see, and 31.61 and 17.21 at 60 minutes. The lesser degree of hemolysis occurring in the Avado group was also indicated by the behavior of haptoglobin that throughout all the CPP was consistently and significantly lower in the patients undergoing conventional CPP. Hemoglobin levels were recorded in the two groups during cardiopulmonary bypass and in the first 12 hours of intensive care unit admission. Figures represent the difference relative to the intraoperative value measured before starting CPP. Throughout the observation period, hemoglobin concentrations recorded in the patients of the Avado group, which is the solid blue line, are consistently but not significantly greater than in controls. Total, to the left, and hourly blood loss were recorded in the two groups during the first 12 hours of ICU admission. The difference in the patients of the Avado group, always with a solid blue line, is most obvious in the first and second post-operative hour, when it reaches statistical significance. Overall, total bleeding was respectively 314.8 milliliters in the control group and 251.3 in the Avado group.